Okay, we are in the chapter 3, statistics, and obviously the first thing we need to do is kind of define what statistics are. They allow us to present data, and so let me again pull this back here, scroll down, and by the way, there is the YouTube for that first screencast-o-matic if you want to see it. So define statistics, I think we kind of mentioned that a little bit. And we're using descriptive statistics, by the way. We're just using them to describe our sets of data, scores, and so on. If you get on to graduate school, you will find that there's a whole nother level of statistics which it deals with prediction. And again, it's all based on probability. They're called inferential statistics, and you get those at the graduate level. And if you want to talk to someone else about statistics, obviously Dr. Wright, Dr. Jones, and Dr. Schmies are doing research now because, again, you use research to present your data when you write articles and publications. So that becomes important when you're in the profession. Not so much important in K-12, but you need to collect data perhaps to justify certain aspects of teaching. Maybe fitness scores are going up, your curriculum's getting better, and again, if you look at the SLOs that I had you take a look at, there's baseline data. And again, that's the process, collecting scores, you're interpreting scores, classify, present, and do something with the data. So, again, statistics, it's all based on the theories of probability. If I would flip a coin, a heads, a tails, and a penny, the odds of it coming up 1 or 50%, one side or the other, 0.5. Now, if I would have 5 straight coins and toss it heads up, if the heads would come up 5 straight times, what's the odds of the next coin flip being heads? Well, it's 50%. So past results don't impact probability, is what I'm trying to say. However, the odds of getting 6 in a row, you take 0.5 times 0.5, 0.5, and that becomes very rare. So first of all, let's start with scales of measurement. There's 4 of them: nominal, ordinal, interval, and ratio. We don't use nominal very much. It's nothing more than numbers. Everybody's got a number. It's a simple, by the way, these are simple and least precise going on to more precise. You simply differentiate an attribute or a property, and again, football jerseys, interstate highways, locker numbers, clicker numbers, how about iPad numbers? You either have number 1 and number 2, but you can't have you could have number 1 and 2, but anyway, they take on one value and one value only. Really don't use much other than frequencies, because sometimes frequencies a number of data occurrences there are. So that's the simplest level. The next one is called ordinal, and the word to remember here, it has a property of order or ranks. One is ranked better than another. This is rating scales and this is ranks. For example, somebody might have done 26 sit-ups and somebody else might have had 20. Well, somebody ranks higher than the other one, the one that did 26. Now, the other thing about ranks, and sometimes this is what you see in football and basketball polls. Right now, the number 1 team in the country was Arizona. It'll probably be Syracuse, because Arizona got beat Saturday night, although don't follow that. And so probably Syracuse will be number 1. Now, the thing about 1 to 2 to 3 is it's not the same distance from number 1 to number 2 to number 3. All it means is number 1 is ranked higher than 2, is ranked higher than 3, all the way down to the top 25. It doesn't mean equal distance, which is the characteristic of the next one, and that's why it's called interval. And again, I'm moving along here up to page 42 already. Interval is more precise because they have equal differences in measurements between the points, the characteristics. The 0 point is arbitrary, but it doesn't represent the absence of any value. Okay? A temperature scale is an example of an interval scale. Okay? If it's 0 outside, it doesn't reflect any absence of temperature. Another one that's there is, by the way, the range, a change from 0 to 4 is the same amount of difference if the temperature changes from 70 to 74. All right, so those 4 degrees are the same no matter where they are. And so an interval is just an equal distance between each point. Ratio is the most precise and most useful of all data, and it has an absolute zero that reflects the absence of any attribute or quality measured, and that's real zero and so on. So ratio data, let me see here. Here's one. Another one, height, I suppose. A child who's 3 feet tall is only half as tall as an adult who's 6 foot. So that type of statement is meaningful. Usually most data measurements that we have in physical education are ratio, but typically you say that this one has an absolute zero that reflects absence of anything. And maybe that's absolute zero temperature. I think that's a different type of scale, though, to tell you the truth. Okay, now we can skip over most of frequency distributions, but I do want to make a point here about how they can be visually represented. Okay, if you follow with me here as far as this simple frequency distribution, 43, if you look on table 3.1, you have a range of scores between 58 and 9. You see the X, that means the number. Frequency means how many, and then of course in the middle row there's 38, and then in the last row it goes from 24 all the way down to 9. So this is a simple frequency distribution. It shows that one person had 58, two people had 45, as you see. Two had 41, 4 had 40, 39 had also 4, so on. That's just a simple frequency for a curl-up score test. Now the next 5 tables all use that same frequency, but it looks a little different. And so the next one is group frequency, and again, you want to have continuous data versus discrete, and you can look at that. Only discrete is only whole numbers, continuous is like 0.5, halfway up, and so on. But again, you don't do curl-ups in 6.5, you do 6 or 7, and so that's discrete data. And of course the range sometimes is, if it's 10 to 11, the range is actually 9.6 to 11.4, but let's not go there. And so if you look at table 3.2, now we grouped it. The top group is 55 to 59. Well, if you look at that other table, there's only 2, and there you see the frequency. And by the way, down at the bottom of that table it says n equals 100. N is always the number of subjects. So this particular sit-up test, it's a curl-up test, had 100 students or 100 subjects. N means subjects, so that's a good thing to remember. And so we're still talking about frequency and distributions, not quite the normal curve yet. But if you turn the page, see, one of the ways you can graph the data is by, of course, the y-axis and an x-axis, the ordinate and the abscissa, if you remember that term. And you have down here below, you have a histogram in table 3.1, figure 3.1 on page 46. That's the same test that we saw on the previous page, the curl-up. Now you can also do it as a frequency polygon, and you see that on page 47. Interesting. See how that starts to look like a normal curve? And there are some of your characteristics that you start to see there on page 47 of the normal curve. Lots of scores in the middle, not too much on either end. Okay, so again, as you have more and more scores, the more numbers you have, the more it resembles a normal curve. And it's going to take me a while, to get to that in a couple minutes. So let's, on 48, 49, and 50, the only thing you need to know there is what's called, there's a curve that's like that, is the normal curve. Properties are coming up in another couple pages. The only ones you have to remember are skewed positive and skewed negatively on page 49. And the difference between the two is with a skewed curve that's positive, there's a few high scores on the plus end off to the right. You see how the tail kind of goes to the right in this where it says skewed positively. And then in the next example, skewed negative, it's extreme low scores, a couple extreme low scores, and you see the tail kind of looks a little different there towards the end of the lower end. And so that's basically called a skewed curve, which sometimes you get. Now the reason I'm going to talk about the normal curve first is let's skip over those types of things and go to the next discussion of the normal curve, which is way up on page 58. On 58, you see some other characteristics of the normal curve. In a true normal curve, now again, the more numbers, the more data points, the higher the n, the more your data will resemble a normal curve. That's the laws of probability. It's very hard to have a normal curve when you have skewed populations, though. And again, think of higher level seniors in college. You know, you'd have a better normal curve if you ranked everybody in high school. You know, you had 1,000 students on something, well, you can get a normal curve. But when you take off the tops and the top half to college, well, now you have a different population, and people sometimes forget that. In a true normal curve, the mean, median, and mode will all line up in the middle there, as you see on 58. And it's at the 50 percentile, which is halfway. Half the scores are below, half the scores are above. You also see there are 3 minus 3 to plus 3 equal distant parts underneath, but they can all contain different levels of scores. However, please note that representation there is the same below the curve as it is over the curve in the middle, if I'm making myself clear, which means that the normal curve can overlap. And that's why they're equal distant. And so those points also make reference to certain issues of variability. And I'll have to talk about that in a minute. And so the next thing I'm going to do real fast here in this 3 or 4 minutes is go back and talk about 2 different things now. Excuse me while I go to the next page. We need to talk about these real fast, because the measures of central tendency and measures of variability, and I'll have to stop after that because I'm only limited to 15 minutes here. So measures of central tendency tell us something about the middle of our data set. The mode is simply the score that occurs most often. By the way, an individual score is usually marked with an X. Okay, usually one score is typically an X. So the score that occurs most often is called the mode. Really don't use it much. So that's why we're not going to spend much time there. We do use the next 2 measures quite a bit. Median is nothing more than wherever the 50th percentile falls. And of course, in a true normal curve, these 3 points line up together. But again, a lot of times we don't have a true normal curve. So it's wherever the 50th percentile is and whether or not you're above and below that. And then finally, the mean is simply the best indicator of central tendency, because every score in my data set, if I have a class of 25, I take all 25 students. I can then sum, I sum the total of X divided by the number of students, and there's my class mean. And so anytime we give you a test, or we take a test or an assessment, and we score it, we can get a measure of central tendency, which is the mean. And so it's the sum of all the scores total divided by n. And so in visualization, it's the sum of X, which is sigma. It looks like a somewhat strange of a E. It's if you know anything about fraternities, it's the sigma fine in the Greek culture. And I'll draw one of those on the board. But it's the sum of X over n. So you take however many students or data points you have divided into sum of X, and that's your mathematical average. That's all it is the average. Those are measures of central tendency. And then of course the next is the measures of variability, which I'm not going to be able to get to very quickly, but the one we use the most is the standard deviation. And we'll have to spend some time calculating that. And the other ones we use are the range, which is simply the highest score minus a low score. And then the interquartile range is the 75th percentile. It's the 25th percentile subtracted from the 75th percentile. And that tells us something about the middle of our 50%. But the standard deviation takes into account every single score in your data set, and more importantly, how far that score varies from the mean. And so these are nothing more than measures of variability, which tell us how variable our data is as far as spread out along the curve, the normal curve. And that